Hello everyone and welcome to the first part of this week's lecture on natural language processing. So in this lecture we will start first with discuss what's language models, what's the difference between a natural language processing model and a grammar model. Then we'll discuss the rules of grammar, how to build them. Then we'll spend some time on discussing parsing, which is starting with a specific sentence, how to identify the role of each word, essentially, part of speech. Is it a verb? Is it an adjective? And then, if we have time, we'll go into augmented grammars and complications of real natural language. So first, language models. So why do computers need to learn natural language processing in the first place? So there are three main reasons. First, to communicate with humans. So in many situations, it's convenient for humans, for example, to use speech to interact directly with a computer. And in that case, it will be important for computers to learn the language. Also to learn from all the text that humans have written. For example, Wikipedia has over 30 million pages with a lot of facts on them. So it would be convenient to just give this data to a computer and have it learn from what's inside. And also to advance the scientific understanding of languages and language use. So using the tools of AI, in addition with linguistics and neuroscience, we can advance all of this. So it's important for computers to understand the language. So natural languages like English and Chinese and so on can't be, even though they have strict rules, but they can be really neatly characterized. For example, there are some judgments that vary from person to person and from time to time when we use the language. So, for example, everyone agrees that not to be invited is sad is a grammatical sentence of English, but people disagree on the whether or not to not be invited is sad. Would that be correct English or not? So there is ambiguity here in natural language. And it's also vague. For example, when you say, that's great, it's not really clear what is great or how great it is. So the mapping from symbols to object also is not formally defined. For example, if we had a strict rule for grammar and language in general, a symbol like, for example, the name Richard must refer to the same person, a one-to-one correspondence. However, we know that depending on where even the name Richard happened in a sentence, it could mean different people and different things. So if we can't make a definitive Boolean distinction between what is grammatical and what is ungrammatical, then the next best thing to do is to look at probabilities. So essentially, what is more likely to be correct and what is less likely to be correct. And that's where language models comes in. So language model essentially define a probability distribution that describes the likelihood of any string to be correct. For example, such a model should say that the sentence, "Do I dare disturb the universe?" has a reasonable probability as a correct string. But the sentence, "Universe dare the I disturb do," is extremely unlikely. So that's what the language model should be able to do here, is to assign probability that reflects the likelihood of a given sentence or part of a sentence. So a language model is a probability distribution then describing the likelihood of any string. Very good. The simplest language model possible is what we call the bag of words model, okay, which is essentially we can say that given a text, can we at least classify what this text falls under? Okay, so here we're not really trying to understand the details of the sentences or what the sentences are saying, but we're just trying to classify a text as, for example, business or weather related. So in bag of words model, we use naive Bayes. So it's a generative model that describes a process for generating sentences. So imagine that for a given category, for example, business, let's say that's my category, we have a bag full of words. And to generate text, we pick a word at random from this bag. So that becomes the starting word of my sentence. And then put it back in the bag and reach and pull another word at random. And this will be the second word in the sentence. And repeat until an end of sentence indicator is drawn, for example, /s. So essentially, this model is clearly wrong because it assumes that each word is totally independent from the other, right? The probability that a word is picked from the bag only depends on how frequent is this probability in the training data. So a word like the, for example, will have a much higher probability of being picked than another word that is not as common. So it doesn't really generate coherent English sentences, but it will allow us to at least do a classification using the naive Bayes form. Okay, so for example, if we pick at random the word stocks and earnings, then this probably means that this paragraph is discussing business. But if we pick words like rain and cloudy, then maybe this paragraph can be classified as related to the weather. So here's a naive Bayes formula on this slide. So we say the probability of a given class given words from 1 through n. So we have a sentence or a paragraph from 1 to n is equal to the probability of the class itself multiplied by the product of the probability of the words given the class. So essentially, we can learn the prior probabilities using supervised learning on a corpus of text, where each segment of text is labeled with a class. So we train our model with each segment of text, so it could be a word or it could be more than one word, and it's labeled with a given class. So a corpus typically consists of at least 1 million words of text and at least tens of thousands of distinct vocabulary words. And these days we're seeing much bigger corpuses than that, with 2.5 billion words in Wikipedia, for example, or 14 billion words in the iWeb corpus. So notice that the process of dividing a text into a sequence of words, this process is used over and over again in natural language processing and is called tokenization. Now, the first improvement to the bag of words model is n-gram word models. So, like we saw, the bag of words models has limitations. For example, the word quarter is common in both the business and sports categories. But the forward sequence first quarter earnings report, this probably indicates that we're talking about financial analysis or in a business category. And if we say fourth quarter touchdown passes, then we're probably talking about football game and sports. So we'd like our model to identifies the difference between these two categories or usage of the word quarter. So what we do is we tweak the bag of words model by treating one option would be to say, okay, let's change our model, take combination of words, like for example, first quarter earnings report, and make that one of the options to be picked at random. That's the entire phrase, first quarter earnings report. But the problem with that is this will make the problem much wider. You can imagine the number of combinations we can make with words and how many more phrases we would add to our bag of words. Now, a more realistic approach is to introduce a new model where each word depends on what has already been picked from the bag. Okay, so we can start by making word dependent on all previous words picked so far. So that's the first equation here. We say the probability of words 1 to n is equal to the product of the probability that each word is picked, given that all the previous words have already been picked. So that's called the n-gram model, and it works well for classifying, for example, newspaper section, as well as for other classification tasks like spam detection, sentiment analysis, and so on. Okay, so in this case, as you can see, to capture all possible interaction is not practical. There will be way too many combinations of sequences of words. So instead, we use a Markov chain model where we say we're just gonna cut our dependence to maybe 1 or 2 words earlier than the word we're currently calculating the probability for. So that gives us special cases of the n-gram model, like the unigram model, which is unigram is essentially the bag of words model, because in that case the word depends on itself. The bigram model, in that case, each word depends only on the word that was picked before it, and trigram, where each word depends on the 2 words that were picked before. So in an n-gram model in general, the probability of each word is dependent only on the n-1 previous words. Okay, so as you can see here, we don't calculate the right-hand side given word from 1 all the way to j-1, no, only from j-1 plus 1 all the way to j-1. Now, other n-gram models exist. For example, a character level model, which can be very useful in language identification. In that case, given a text, determine what language it's written in. Even with very short text like, for example, hello world, the n-gram letter model can identify the first word as English right away by just looking at the sequence of character HELLO. And these models are very accurate, actually achieve accuracy in classification over 99%. Character models are good at certain classification tasks, like deciding, for example, if a given word is a drug name, or a given word is a person name, or a city name. So even though we might have never seen these words before, but an n-gram model trained on a character level to predict the next character can easily be trained to tell if that's, and generalized to tell if that's most probably a city name or a person name. Okay, I will continue in the next part.